Hi, and welcome back to the stream. We are playing Nand Game, which is a game that sort of goes through the Nand to Tetris course in a graphical fashion. It's at nandgame.com, and you can try it whenever you like it. Last week, we built some logic gates, and we did some arithmetic combinatorial logic, and we built a mux and a demux. I'm going to continue to use my own terms for these things rather than theirs. This week, we are going to introduce sequential logic. We're going to be introducing latches and data flip-flops, registers, counters, and RAM. And so these are very different from combinatorial circuits in that they have values that change over time. So let's take a look at the latch. Components built until now have no memory. Your mission this time is to build a latch, a component that can store 1 bit. Interestingly, this is the one place where Nand Game actually goes beyond Nand to Tetris. Nand to Tetris, because it's not really an electronics course, it's really a computer course. They just give you a data flip-flop. They just give you a DFF as a core component that you can use. But in this game, we're actually going to build a latch. So a latch is fairly simple in this context. Whoops, let me get my window out of the way there. Okay, so really to build a latch, if I remember this correctly, all we need is a mux. So what do we have here? We have a store bit, which is going to tell the latch to store and emit that value. If store is 0, then the data value is completely ignored, but we still emit the previous value. All right, so the store bit is pretty clearly the select input on our latch, because that's what's on our mux, excuse me, because that's going to determine what the behavior is. So if store is set to 1, then we want to both store and emit the value D. A little bit of a graphical bug there. Right, and you could see here that that is being emitted. Now the tricky bit here, is that if store is 0, we don't want this to be 0. We want it to be whatever was previously stored in this. And so to accomplish that behavior, what we're going to do is we're going to take the output of this mux and we're going to wire it back in to the mux itself. And so I think this will do that. Right? We can change data to 0. 0 is in the mux. That worked. Now, if data's 1, 1 is in the mux. We are still doing 1 out there. So I believe that should do it. Congratulations, we have successfully built a latch. This is really, in electronic terms, not not an actual latch. It's a little more complicated to build components that have to stabilize over time, but this is a reasonable abstraction for a web browser game. So let's go on to the next level. Using latches, you can build a circuit that changes its state over time. And here they explain that since state changes are not synchronized across the circuit, you can't predict the order in which they're going to happen. And so we're going to use a clock signal. And what the clock signal is going to do is basically, this is how much time the circuit has to stabilize. And only when the clock signal reaches a certain place do we actually read the circuit in that. Are we willing to use the value? So our task here is to build a flip-flop, which stores a bit when the clock signal is 0, but only starts emitting the stored bit when the clock signal changes to 1. All right. That should be easy peasy if I could actually, oh, you know what? This is yeah, there's something weird. If you have the windows at certain sizes, some of the controls don't respond. Hopefully that won't cause us too much trouble here. Right, we have some specifications over here. When store is 1 and clock is 0, the value on D is stored, but the previous value is still emitted. So this is behavior a lot more similar to what I think of as a latch. because you don't have a latch that you're just going to be able to read at any time. When the clock signal changes to 1, the flip-flop starts emitting the new value. Okay, well, first of all, we're clearly going to need a latch, whatever happens here, because the latch is the thing that the flip-flop is going to work from. And I think that because we have 2 clock signals here, we're actually going to need 2 latches. And what's going to happen is that our data is going to march through the latches. So on clock signal 1, the value is going to march into this latch. No, sorry, on clock signal 0, it's going to march into this latch. And then on 1, it's going to be in here, and at that point will be emitted as long as what? Right, we want this emitted on clock signal 1. So that means I'm going to wire up. Oh, look at that. That's terrible. Well, you can see that this line is headed towards clock. So when this is 1, then this latch is going to be active and it's going to emit its value. So that leaves us with what happens here. Well, do we just want this on? Yeah. Okay. So we want this to emit or to eat this on clock signal 0. You could see for some reason they decided not. Oh no, here it is. There is an inverter. All right. So clock signal 0. All right. So this is clock 1. This is clock 0. We're going to wire up this latch to. No, we're going to wire up. It's not just this value. I was going to say that we wire up this to clock 0, but then we're completely ignoring the store flag. So we actually need an AND gate here. And we will store when the clock is 0 and, come on, you can do it, and this is 1. Did this actually connect? Yes, it did. Oh, that's a terrible bug. Let me see, I'm going to change the size of this window and see if, okay, that's a little better. Now we can actually see. It's harder for me to read, probably harder for you too. All right, let's see. So if store is 1 and data is 1 and clock is 0, then this is 1 and this still has 0. We're going to click the clock to 1. This went down to 0, which makes sense because store is 1. And our 1 is out here. So I think that's correct. Let's see what happened. All right, and it's still telling me it's possible to solve with a lower number of NAND gates. As I said last week, I'm really not going to worry about that at all. All right, so now we have to combine 2 of these DFFs we made to store and retrieve 2 bits of data in one operation. And if you could store 2 bits of data in parallel, then you can store 4 or 8 or 16 or 32 or 64. And this is pretty common. Most of the games actually do exactly this. NAND to Tetris actually makes you build up the 8-bit or 16-bit operations. I think they mostly go to the 8 level. All right, so we want 2 bits of data. Well, that means we're going to need 2 DFFs no matter what. You know what, let's make this nice and neat. We'll put these, how type A do I want to be? Can I move these? No. All right. Wire up our outputs to those DFFs. Likewise, we have data inputs. That makes sense. We have clock inputs on these DFFs. So we could wire those up. This one is this is literally just plumbing, I think. I don't think there's any trick to this one. Right, and you could imagine if this was a 16-bit output, we would have 16 of these lined up. Our least significant bit is on the right. Our most significant bit is on the left. Does it work? Yes, it works. Congratulations. We are so smart. All right, so now we're going to build a counter which increments a number at each clock cycle. This is what's going to drive our CPU. All right, so what are we going to need? Well, clearly we're going to need our register, right? Oh, look at that. It's a 16-bit register. It built it for us. Well, if we're going to be incrementing by 1, we're going to take our incrementer that we built earlier. And you could see here that they expanded this incrementer to 16 bits for us. So that's very nice. We've got a clock. We'll wire up the clock. All right. If ST is 0, then the previous counter value is incremented with 1. If ST is 1, then the input X down here is used as the new counter value. Well, that sounds a lot like a mux. So let's go ahead, and we know that ST is our selector on our mux. We know that if ST is 1, the input value X is we use, so that's the 1 input, the high input on our mux. And then that just leaves us with this 0 input. If 0, then the previous counter value, so that's this is a register, is our counter, is incremented. So we're going to put this up here, right? So this up here is the incremented value. We'll take our D0. Can I make this curve neatly? Nope. Oh well. Oh, that's terrible. All right. We'll just put that over there, looking all cross-eyed. That just leaves us with, let's see. Right. So in either event, either this X becomes this X up here, or this becomes the X. So in either event, we're going to be getting the output of the mux. So then the only thing we have left is here. Right. So this is a little weird because although this register has this store flag, in reality, we are providing a number no matter what. So we want this store flag to be 1 all the time, no matter what. So what we'll do is we'll take a 0 bit and we will invert it. So this is always going to be 1. All right, I think this is correct, as is. Level is not correct. The current diagram does not comply to the specification. And then they give us the tests here, and they tell us what they think they're going to be. And somehow we have made a mistake. What did we do? Okay, set ST to 1, set X to 7, and clock to 0. This should set in to, oh, yes, I forgot to plug it in. There we go. The interesting thing here that I want to point out is visually on screen here, we've got 1, 2, 3, 4, 5 components plus wires. This 5-component circuit, which looks fairly simple, uses 738 NAND gates. I mean, that's amazing, right? And that's how quickly this all scales up, and it's why using this visual abstraction I think is pretty powerful. All right, so now we are at the final level for today. I'm just going to do the memory stuff today. I figured I'd do a little mini episode. I didn't want to be here for an hour. So now we can store a 16-bit word in a register. We can get more memory just by stacking these registers. Since we use memory addresses. We have to use 2 registers and address them using a single bit. After reading this, I'm not sure I fully understand this, so let's go to the spec over here. Sometimes the spec is a little easier to read than the tutorial text. Build a memory unit with two 16-bit registers, which is addressable and writable using a 1-bit address. Address indicating which storage unit we're accessing. Store indicate if we want to write to the unit. That's a data value. All right, so this is basically building up a RAM bank. That's what we're saying here. So again, we want two 16-bit registers. They tell us that outright. All right. And we're going to be choosing between them. Well, that sounds like a mux. So let's go ahead and call this one the high bit, this one the low bit. It's not high and low bit because we're actually selecting between them. D0 and D1 is fine. X and Y is what I usually call mux inputs. This time we will remember to plug it in at the very beginning. And I'm going to go ahead and say that this address field down here is probably the selector for that mux. And thank you very much for putting a big ugly line right over my register. That's super helpful. All right. So now we need to get data into this mux. Well, the clock signal's a freebie, right? So we can just wire those up. And that's going to be the same for every device that uses a clock in the system. So the clock will always wire up to everything with a clock. So here, we need these things. What do we need? We want to store X in the register that is selected, but equally, unlike the other one, we don't want to store X in the other one. We don't want to overwrite the value of a register. So in this case, we actually, I think, need a demux, where this X value is the data in the demux, and that is destination 1, or destination X, and that is destination Y. And that just leaves us with this switch. And again, I think it's... no, I think I've messed up. This does not seem right to me. This is not going to work. Oh, I'm a dope. Okay, so we're going to break those. No, so if you remember, I said it was weird in the last exercise where we were always setting store to 1 and we were always just going to overwrite the value no matter what. Well, here we're going to do the exact opposite, actually. Right? We're always going to send X to these registers, but we're only going to make that register writable if this store flag, if it's the address has been selected, and the store flag is in fact the data payload for this demux. Let's try it. So we're going to say yes store. We're going to say, let's say FFFF, and we're going to say address 0, clock 1. Okay, and 0 is our address that's selected. Okay. Let's set that back to 0 just to clear it out. And FFFF. And this time, let's set our address to 1. You can see the wires there are telling us that this should work. That looks wrong to me because it actually... Did I make a mistake here? I must have made a mistake here. I feel like I have something wired up that shouldn't be wired up. What's going on here? Right? Store 0. Let's try this one more time. 0, 0, 0, 0. We'll tick the clock. Oh, see, that was right. That got... Oh, you know what? I didn't actually clear address 0, store 1, tick the clock. Okay, actually, I think that's right. I think I just spent 5 minutes worried about nothing. Look at that. I was worried about nothing. Great. So we have built 2-bit addressable RAM, and that can be expanded up to as much RAM as one needs. So let's go back, see what we have to do. So next week, we're going to take all of these components and put them together into an ALU and hopefully explain how opcodes work with that ALU. Well, I hope you enjoyed this, and see you next time.